Hello, I'm Lihang from Tsinghua University. I'm very happy to present our paper, Automatically Generating and Improving Voice Command Interface from Operation Sequences on Smartphones. Using voice commands to automate smartphone tasks can effectively augment the interactivity of existing apps. For example, when you want to make a video call to your friend, you have to carry out a 5-step operation sequence, which may be inconvenient or even impossible in some cases. With a voice interface, you only give a verbal command and the task is executed automatically. However, creating voice interfaces requires tremendous effort, especially in understanding user commands due to the flexibility of natural language and the large amount of GUI tasks. In this paper, we propose AutoVCI, a novel approach that generates voice command interface automatically. The generated VCI understands and executes user commands with operation sequences only, without corpus, programming, or handwritten rules. The generated VCI has two distinct features. First, it automatically maps a voice command to smartphone tasks and fill in parameters, leveraging the GUI data from both operation sequences and user device. Second, it launches an extra Q&A dialog to confirm the intention from the user in case of unmanageable ambiguity. The VCI also learns and informs from interaction. It accumulates the history results to annotate the user's command, improve its semantic understanding ability, and simplify subsequent interactions. First, we will introduce how the designer generates a VCI with our approach. The only input for the generation is the operation sequences. We provide a tool with which the VCI designer can collect the operation sequences by manually carrying out the tasks on the smartphone. The collected data will be uploaded to our server automatically. Our approach calculates semantic metadata for each operation sequence. It first identifies parametric operations from the sequence. We classify the parameters into two categories, list parameter and text parameter, and propose an algorithm to identify and classify them. Second, the VCI calculates a semantic factor for each operation sequence, which is composed of a word factor, a sentence factor, and a BOW factor. The word factor and the sentence factor are calculated with a pre-trained BERT model. The VCI generation finishes after the semantic calculation. Next, we will introduce how the generated VCI works after the user gives a verbal command. The first step is intention identification, in which the VCI determines the target task to be executed. The VCI converts the user command into a factor using the same method as calculating the task semantic factors. It then calculates the cosine similarities between the command factor and all task semantic factors, and takes the zero normalization results as the final similarity scores. Tasks with positive similarity scores will be added to the candidate set. The VCI calculates the bag of words factors for the candidate tasks, constructs a decision tree, and starts a Q&A dialog accordingly. At the beginning, the VCI is at the tree root and asks, "Do you need to click WhatsApp?" The user answers, "No." The VCI moves to the left child, asks, "Do you need to click video call?" The user answers yes. The VCI moves to the right child, which is a left node, and filters out the target task. The VCI finally proposes a confirmation question with a detailed description of the identified task. The question can be first simplified during the semantic accumulation. If the user answers yes, the intention filtration finishes. The next is task execution and parameter identification. The VCI simulates events to the user's smartphone according to the operation sequences to achieve automatic task execution. When encountering a parametric operation, the VCI identifies parameter values from the command. For list parameters, the VCI compares the all texts in the list with the user command, and the common words will be identified as a parameter value without any extra dialog. For text parameters and list parameters with text matching values, the VCI proposes parameter questions that are composed of information from the last and the next operation. The answers to the questions are directly the parameter values. After identifying parameters, the VCI continues task execution until the end. The VCI accumulates semantics from the history command understanding result and improve its semantic understanding ability. The VCI first generates a template by removing the parameter from the command. It then calculates a factor for the template, which is utilized to update the task semantic factor. Semantic accumulation can simplify subsequent interactions in three aspects. First, it can simplify confirmation questions. Second, the VCI can match the command directly with a new template. Third, it can decrease the number of intention recognition questions. The target task can get a higher similarity score with the updated factor. As a result, the VCI may skip the intention filtration, or the depth of the target task in the decision tree may decrease. We implemented the approach on an Android phone and conducted a user study and an offline evaluation. 16 users participated in the first phase, and each of them finishes 40 tasks with random order. Users could carry out JiaHui tasks using the automatically generated VCI with a high success rate. Semantics accumulation decreased the number of extra questions and improved the interaction efficiency. The user also gave positive feedback to the generated VCI. The second phase focused on larger scale semantic accumulation. The VCI accumulated semantics of 8 tasks 77 times. We calculated the metrics in a 64 sliding window to reverse the trend. The number of extra questions per command dropped 75%, and the template match ratio increased 5.6 times. We finally conducted an offline evaluation with data collected during the user study to evaluate our semantic understanding approach further. With a pre-trained BERT model only, the top 1 accuracy is less than 80%, and some tasks were poorly recognized. This result implied that it was necessary to start extra dialogues to help understand user commands. We tested different Q&A strategies to recognize user intention. The result showed that the weighted decision tree required the smallest average number of conversation rounds compared to the unweighted decision tree and the similarity ranking. Finally, we evaluated the improvement of various metrics resulting from semantic accumulation. We mainly focused on 3 metrics: the template match ratio, the similarity score of the target task, and the number of extra questions. The results showed significant improvements in all these metrics, which you can find detailed description of in this paper. We also compared different semantic accumulation mechanisms and found that factors and templates are naturally complementary. All mechanisms showed significant improvements compared to both mechanisms that only accumulated templates and only updated factors. Thank you for your attention.